In this video, I'd like to talk about the Planck or Planck-Einstein equation, the energy for quantum particle equals h bar times omega, and the Broglie relation, the momentum of a quantum particle equals h bar times wave vector. You know they are very fundamental equations of quantum mechanics. In particular, I want to talk about the connection of these equations with special relativity. So, in 1900, the German physicist Planck introduced his relationship h bar omega in the treatment of a black body radiation. Imagine this picture, a picture of a black body. Planck supposes that the atoms of the cavity of a black body to be oscillators with discrete energy with quantized unity h bar omega, where h bar is a Planck constant over 2π Greek. But the electromagnetic radiation in the cavity was still considered by Planck classically, according to the Maxwell equations. However, in 1905, Einstein introduces the quantization of the electromagnetic field in order to explain the photoelectric effect. Schematically, the expulsion of electrons from a metal by the light. To simplify, the electromagnetic plane wave, the angular frequency omega, were composed according to Einstein by particles with energy given by the Planck formula. In 1970, always Einstein shows that two photons, particle without rest mass, that is, rest mass equals 0, by special relativity it is possible to associate a momentum P equals h bar times wave vector. The next step of a quantum revolution was performed by the French physicist Louis de Broglie in his PhD thesis in 1924. He makes the assumption that every particle, also different from photons, could share the strange dual property of wave and particle with the light. And the fundamental hypothesis of his dissertation was to consider true for all the particles, not only for the quanta of light, the Planck-Einstein relation, so also for particles with rest mass different from 0. Then, with the special relativity and other assumptions, he finds his famous relation P equals h, the Planck constant, over lambda, where lambda is the wavelength of a wave associated with a particle. Now in this video, first I want to show an alternative deduction of the Broglie relation obtained directly from the Lorentz transformations, the Planck-Einstein equation. Then I want to show how a special relativity puts constraints on the formulas that may connect energy and momentum of a particle with wavelength and frequency of a wave and a wave vector. In particular, we demonstrate that a question like the Broglie and Planck-Einstein are the only relations allowed by special relativity when we assume that the momentum of a particle and the wave vector or a wave have the same direction. Einstein showed us that deducing the Broglie relation from the Planck equation for particles without rest mass, that is m0 equals 0, is very simple. In fact, it's enough to consider the relativistic equation between momentum and energy for the photon E over c, and putting the energy equals the Planck constant times the frequency in this equation, recalling that lambda is the speed of light over the frequency, we quickly obtain the Broglie relation. Indeed, putting this equation here, P is the Planck constant times the frequency over c, but this factor is 1 over lambda, so we obtain a Broglie relation again. An elegant and general way to derive a Broglie relation for any massive that has mass different from 0, or massless particle that is m0 equals 0, can be achieved using directly the Lorentz transformation. Let me show that. Let me do the following assumptions with the Broglie. First, each particle is associated with a wave, and second, in every inertial frame a relation of Planck or Planck-Einstein equals h bar omega, where E is the energy of a particle and omega is the angular frequency to pi time frequency, and h bar is h over 2 pi Greek relativistic invariant. We want to show that according to special relativity and the previous equation, it follows necessarily with the Broglie relation, that is for the demonstration, let's introduce let S and S primed be two inertial frames in relative motion, and for simplicity the frame S primed have parallel axes to each other, y axis, and this is the x axis, and that at a time t equals t prime equals 0, the origins O primed of the coordinates coincide. Moreover, we suppose S prime moved with respect to S with speed v less c along the direction x-axis, and the direction of wave propagation to be along such axis as in figure. That is, we assume that in both frames the Planck relation applies to any particle. That is, let me change color. And in S primed. We introduce for a particle of a wave with 4 momentum p and a wave 4 vector k, respectively. P equals E over C and a p vector, and 4 vector k equals omega over c and wave vector, where the wave vector k has modulo 2 pi Greek over lambda. The Lorentz transformations for the 4 momentum and wave 4 vector are: for the 4 momentum, E primed over C equals gamma times E over C minus beta p x, p primed x equals gamma px minus beta times E over C, and for the other components, of course, and pz primed equals pz, and for the wave 4 vector, omega primed over c equals gamma times omega over c minus beta times kx, then k primed x equals gamma times kx minus beta omega over c, and then the other components. And then with the usual beta is the speed of a frame s primed with respect to s over c, and gamma is the square root of 1 minus beta squared, that is. So these are the components in the frame S prime, and these are the components in the frame S, so on. Okay, let me take the first two equations of a Lorentz transformation, that is this and this. I write them again. Prime over C equals gamma times E over C minus beta px, and omega prime over C equals gamma times omega over C minus beta kx. And multiplying the second equation by the Planck constant h bar, you obtain h bar omega primed over C equal gamma times h bar omega over C minus beta times h bar times kx. Now, subtracting side by side the two equations, 1 and 2, and for which, because of the Planck-Einstein relations, the two frames, we have E equals h bar omega and E primed equals h bar omega primed, we get, so subtracting side by side the two equations 1 and 2, we get prime over C minus h bar omega primed over C equals gamma times E over C minus h bar times omega over C minus beta p x plus beta h bar kx. And because of Planck-Einstein relation, this term is 0, also this term is 0, and we get gamma beta times px minus h bar kx equals 0. Now, if we exclude the condition gamma times beta equals 0 when the relative speed with frames S and S prime is 0, the last equation is only satisfied if px equals h bar times kx. So this is the de Broglie equation for the x component of a momentum. And we point out, as the just given demonstration holds for particles of any mass, while de Broglie's demonstration only holds for particles with non-zero rest mass. And this equation can be easily generalized to other components of the momentum and wave vector, considering a general orientation of the wave vector with respect to s, that is